Okay, so we're going to look at moving our vectors now from kind of the real world and open space to the Cartesian plane. Just a quick review of a couple things here. Vectors have direction. So when we talk about something, our speed being 80 kilometers per hour, that of course is not a vector. A vector has to have a magnitude and has to have an established direction. The equivalent of that would be if I drive my car 80 kilometers per hour towards the north. I drive 80 kilometers per hour backwards, or if I have some sort of go-go gadget car and I'm able to go 80 kilometers per hour straight up. Okay, so any of those are velocities now because the direction has been established. Otherwise, the actual magnitude is the same as the speed, but as soon as I start talking about a direction, we're talking velocity. Same sort of thing, talking distance versus displacement. Distance 700 meters, but that doesn't tell me a whole lot. If this were a path that I followed, I've gone 300 meters towards the east, then 300 meters north, then 100 meters east again. Essentially, I have three different displacements, a total distance of 700, and an overall displacement of 300 and 400. So an overall displacement of 500 in this direction, which I don't actually know, but is somewhere in the 40 degrees. So something like north 50 east. I didn't actually do that calculation, but the understanding is that that's the direction there. That's the magnitude of the overall displacement. The actual distance traveled, the distance walked or whatever, was the 700. Okay, so do understand that while often our vector quantities have the same magnitude as the equivalent scalar quantity, they don't always. Now, the big key here is to recognize as well that, or in moving forward, the big key is recognizing that whatever our overall vector value, there is a horizontal and a vertical component to it. As far as moving things onto the Cartesian plane goes, that's how we're going to establish, that's how we're going to identify our vectors. In this case, just kind of counting across, I have 1, 2, 3, 4, 5, 6, 7, 8 in that direction, or I've gone 8 in that direction. I've gone 1, 2, 3, 4 in this direction. And so to describe this vector, or to establish the size of this vector, I write it as 8, 4 in square brackets. This is an explanation of the vector. The actual size of the vector, if I want to find it, I can sort of consider this a right angle triangle, of course. The size of it, the size of the vector. Let's not write that. Let's call this vector V. And there's again the naming of the vector. The size of that vector, magnitude being absolute value, sort of recognize the symbol there, is going to be the square root of 8 squared plus 4 squared. Okay, so just using the Pythagorean theorem here, square this, add them together, take the square root to establish the size. Just a couple of key points kind of as you get into the work. We'll be working on these for a couple of days. The first day will be basically just understanding sort of stuff. We'll do a little bit of application in the next assignment, or the next set of work. Okay, so first thing you'll sometimes see things like this. Now, the handout that you've got talks about the unit vectors, I being 1, 0, so it's a vector that is exclusively in the horizontal direction. J is a vector in the vertical direction. In both cases, unit vectors, so they have a size 1. And just sort of when you see this, it's not a syntax that we use as commonly at this point, but what this is saying is I have -1 in the x direction. I have 3 times this vector, so I have 3 in the vertical direction. That is the same as a vector written this way. And so question 2 I've assigned, but it's really just try a couple and make sure you know recognize what the syntax is saying. This is -1 in this direction. This is 3 times the vector, the other vector. This vector happens to be 1 in the vertical direction. And so overall, my new vector is this, or my vector rewritten in Cartesian form is this. 5j means there is nothing in the I direction, or in the x direction. There's 5 in the vertical direction. And of course, the equivalent to 5j would be this. This one is 6 in the I direction, -1 in the y direction, or the j direction. And so 6, -1 becomes that vector. Okay, so just sort of when you see those, understand that they are exactly the same as these. Of course, we can go from this back to that as well. And then what will carry over from that is this means 3 times j. So it's saying that the vector that's resulting here, or at least in this case, the part of the vector that's resulting here is going to be 3 times bigger than whatever it was before. Similarly, if I was to write something like 3v, it means whatever my vector is there is going to be triple the size. So if my vector was established to be right here, then 3v would be essentially 1, 2, 3 times as big, and in the exact same direction. So exactly what you'd expect it to be, 3 times the existing one. And in both cases, my intent there was to have the vector kind of heading in that direction. Okay, so whatever our values are, basically this is saying triple them. If you've got a drawn vector, triple its size in the same direction. A couple other little things just to sort of make sure we don't confuse them. If I look at these, the vector is written with square brackets. Points from before were written with round brackets. The same syntax holds now. And so anything written with square brackets, we will assume is, what we want to assume is a vector. Anything written with round brackets is a point. And so given that, when you run into questions that have something as simple as a is equal to, you'll know that because it's given with round brackets, it's talking about there's a point there where those are the coordinates. If it's given square brackets, it's telling you that we're talking about the vector. And the same will be true with anything you give me. If you have square brackets, I will presume you're suggesting it's a vector. If you give round brackets, I'm going to assume you're giving me a point. And I will sort of establish that as the criteria right here. And that'll be kind of how we do our marking as well. And then last kind of quick comment here, collinear vectors, just a couple of definitions. I just pulled this right out of the questions that are assigned, so this is incomplete here, but you'll see it when you get to question 5. Collinear vectors, you see the word line in there, and the prefix collinear vectors lie on the same line. Essentially, any 2 vectors that go the same direction, or I shouldn't say that, any 2 vectors that are on that same line are collinear. They don't have to be in the same direction. So I could have a vector kind of covering this basic spot. I can have another one that is going this general direction. But again, essentially, if they were placed on top of each other, or they can be placed on top of each other, let's say, so that one covers the other. And equivalent vectors are just 2 vectors that have the exact same size and the exact same direction. So looking at the Cartesian plane, it should be pretty easy to see that this vector and this vector are the same size, same direction. So establishing whichever points for it means we'll have the same thing. So I'm going to stop there. Again, the work will be should be quite easy, I think. Just sort of recognizing the syntax, understanding the difference between points and vectors, and being able to recognize them.